So we're getting ready to start. Welcome to presentation on runtime kernel patching on Mac OS X. My name is Bosse Eriksson, kind of hard to pronounce for you Americans and non-Swedish people. I'm a security consultant at Swedish company BitSec, and I break stuff for a living. And recently I've been looking into Mac OS X rootkitting techniques. So that's short about me. We only have 20 minutes, so I'm going to speed this up, but the basic talk is going to look like this. Short intro about rootkits, OS X, BSD and the XNU kernel, runtime kernel patching in general, what makes runtime kernel patching specific for OS X, and I'm going to demonstrate a proof of concept rootkit for OS X, also some basic detection technique for this, and we'll take questions if we have time. So I'm going to start off. So I'm pretty sure most of you guys know what a rootkit is. Well, basically it's a program for access retention. It's like not an exploit or a Trojan horse. Like it doesn't grant you access to a box, so you don't own something with it. Also, you don't send it to a person and have them like run it. It's something you run on a box you own to retain access to it. Typically requires root access and it provides stealth techniques like hides files, processes, sockets, and so on. Basic types of rootkits are user space rootkits and kernel space rootkits. That's the main categories. The user space rootkits are kind of easy to implement and therefore easy to detect. The kernel ones are a bit harder to implement and much harder to detect if they are done properly, since you are at the kernel level of the OS and you can manipulate pretty much anything you want. So this is a simple demonstration, just so you get this right. This is when you get owned. That's the exploit right there. And the bottom line is that's when you stay owned. That's the rootkit. So just to get this straight, it's require root access. So example of rootkits. Well, user space, like various evil patches to PS, netstat, LS, and you can do also binary patching like SSH daemons and stuff. Pretty basic stuff. The kernel ones, there are a few out there, public, private. We have Phalanx by Rebel, which is a kernel patching rootkit for Linux 2.4. Uses devmem device to patch syscalls. Suckit by SD, which is a classic, one of the first public rootkits who used this runtime kernel patching. It's for Linux 2.4. Also, later version Suckit 2 for 2.6. We have Knark by Switchgun and Creed, which is a Linux kernel module for Linux 2.2. And took syscalls by patching the kernel via an LKM. And also we have WeaponX by Nemu, which is, I believe, the first public OS X kernel rootkit. But unfortunately it stopped working at OS X 10.3, and there hasn't been any public OS X rootkits since then, I believe. So short intro on OS X and the XNU kernel. The XNU kernel is the kernel of the OS X operating system, and it's built on both BSD and Mach technology. Mach is the microkernel which runs in the bottom of the OS, and you also have a kind of BSD layer in there, and they're both responsible for different stuff. This is very abstracted, but the BSD layer is responsible for networking, processors, and POSIX API, and the BSD syscalls. So you can basically do like any POSIX stuff on OS X without touching the Mac layer at all. And the Mac layer handles like kernel threads, interrupts, memory management, scheduling, and so forth. We don't have the time I want to dig into this, but this is the basic of it. The XNU, like any modern operating system, supports modules. On Linux you have LKMs, BSD has KLDs, and OS X has KEX, like kernel extensions for device drivers and so on. So you can extend the kernel at runtime and adding new code to it. And this has been the primary way to subvert the XNU kernel. Like the rootkit I mentioned, WeaponX, uses kernel extensions to patch it. But I think that's kind of all that's been done. It was a talk last year on Black Hat by Jesse, I can't pronounce his last name. He did same thing with KEX. That works for every new release of OS X. But we're going to skip the KEX part and we're going to runtime patch the kernel. So runtime kernel patching is basically subverting the kernel without use of kernel modules. because that's like the basic entry point in the kernel for normal rootkits, like Weapon X. And we were going to do like hooking system calls to stay hidden and implement various backdoors in the running OS by just patching the kernel directly in memory. And you can also manipulate various kernel structures to do all kinds of crazy stuff if you want to, but I'm going to show you some basic examples. This is basically function hooking for those of you who doesn't know it. It's kind of a man-in-the-middle attack between two functions. Let's say function A calls function B, but instead of function B getting executed, the evil hook function gets executed, and then it executes function B and passes on the return value back to function A, so it's like a transparent man-in-the-middle attack. Function A sees the result from function B, but various other code can also be executed in the hook. So that's the basic idea of function hooking. Runtime kernel patching is nothing new. Like I said, it's been done. I think the first occurrence was the Suckit rootkit back in like 99, which did this on Linux. And the basic idea is you allocate kernel memory from userland, you put your evil code in the allocated space, and you redirect a system call or any other function to this memory area, and then you get profit, because you can do like whatever you want. So, normal way to do this is for Linux. You find a suitable system call handler, like set hostname, that is rarely used. You back up the system call handler, you redirect the handler to kmalloc, the function in the kernel, to allocate memory, and then you execute the system call, and kmalloc will be executed from user space, and you have your memory. And then you restore the system call handler. But that's kind of a lot of work, so we're going to do this a bit easier. OS X is very hacker friendly, by the way, since it provides an API for this. You can use various functions exported by the mock layer to do this evil stuff, and all you need is root. So there's a couple of functions here: VM read, VM write, and VM allocate. I'm not going to go into this like too deep, but basic, they read, write, and allocate memory in a process. So you're going to see where this is going. This is some basic analogy of the mock kernel. The mock part of the kernel of XNU has tasks, which is a logical representation of an execution environment. Fancy speaking, it contains one or more threads, and a thread has its own register and scheduling policies. So we're not going to go too deep into this because we don't have time, but you have ports. Ports is like a message communication channel. It's used to send messages between processes. That's basically all you need to know for this. So here we have a simple function using this for reading memory. I don't know if you can read that, but you just call task for PID, and you could specify PID 0, which is the XNU kernel running in the OS X operating system. And what you get there is a port to the kernel. You remember the communication channel? And all you need to do is use this function VM read, VM write, and VM allocate, and you can manipulate the kernel's memory space. It's that easy. It's literally like 10 lines of code to read kernel memory as root. It's pretty awesome if you want to rootkit a machine. Here's the same function, but for writing kernel memory. Same thing, task for PID, VM write, you're good to go. Also for allocating, it's just a one-line change. So, OS X has a global sys entry array which holds a structure for each system call available in the kernel. Its maximum is 427, goes from 0 up to there. Each entry has this structure which contains the system call arguments and also a pointer to the system call handler, which is the function that gets executed when the system call is called. So that's our main target we're going to patch. So to do this, we need to locate the sysentry table and patch the system call handlers. This guy, Landon Fuller, he developed a really nice method of doing this with a kernel extension to enable ptrace for certain Apple applications. His method was like this. Since the number of system calls is an exported function in the kernel, called nsysent, number of sys entries, you can calculate from that an offset to the system call table, sysentry table, and that's static. It's 28 plus 4 on I386. So you just add to that and you get to the sysentry table. I can mention before 10.3, the sysentry table was in self and exported, so you could access it directly from a kernel extension, but it's not anymore, so you can't patch it directly. You need to locate it in memory. And that works pretty good for Kext, but as I said, we don't want to use Kext. So to do this from userland, we just need to locate the number of sys entries in memory. And on OS X, the kernel image is on the file system called mock kernel in /, and it contains the nsys entry symbol, which can be resolved by parsing the mock O binary. And you take that symbol plus 32, and there you have it, the sys entry table. So you don't need a kernel extension to do this. And yeah, as I said, I was thinking about doing some Mac O parsing here, but we don't have time, so I'm going to skip it. The kernel is a universal Mac O binary with 2 architectures, I386 and PPC. So just read up on how the file format is, and you can parse it pretty easy. I even have some tools to do that. I'll give to you later. So basically, the modified function looks like this. It's S2A resolve. It's a library I threw together to resolve symbols from the kernel. So we don't change anything. We just resolve it from the kernel on the disk. So now we have located the sysentry table, which holds all the system calls in the OS. We can read, write, and allocate kernel memory, which is good. So now we're just going to get down to the dirty business. So it looks basically like this. We have the sysentry table, which contains all the system calls. Normally it points to like 001E425C. I think that's for one reversion back of the XNU kernel. It points to open for the OpenSys call. What we're going to do is we're going to modify that structure and point it to our address of our choosing. Not necessarily a dead code, but an address where we have this function here, where we then have a function pointer, which we will execute and return. So we can do evil stuff in between, transparent. So I'm going to show you like a proof of concept rootkit I threw together for this. It's called Mirage. It's a cheesy name, I know it, but it resolves symbols from the XNU kernel and hooks system calls using the named functions. It's not detected by check rootkit, but I don't know any serious rootkit which is detected by check rootkit. So demo time, and I'm not going to do this live. I have videos since I'm a chicken. So basically, we compile the rootkit, we patch the kernel with the install. As you see, PID11 here is visible. It's the directory service. We install the rootkit, patch some syscalls, and PID11 is gone. We uninstall the rootkit, and PID11 is visible again. So that's basically process hiding. Thank you. There's more. We have an open backdoor here. It's kind of messy. I'll take it later if we have time. This is the TCP input hook. The basic idea of this is you send the infected host a trigger packet, and it looks for patterns in the TCP packet and then executes stuff you want. So on the top here is the infected host, and the lower window is the attacker. We build a rootkit. We install it, hook some system calls and the TCP input handler. That's a client for a connect back shell on a, this is the same host, but it could be a remote host. And I just send a packet to port 1337, and there you have it, root prompt. And as you see, we're root. You don't need to connect to the port, actually. I just use netcat because it was easy. You can do that with any kind of trigger, like in the TCP header. Really easy. You just need to modify it. So, detection. Well, how do you detect these things? Like if you've been infected. It turns out it's pretty easy. You just compare the sysentry table in memory to a known state, right? But I think everyone in here knows that that's just not the case every time, because there's like a million ways to bypass this comparison. But I'm going to show you it anyway because it works. But any serious attacker would not make this work. So yeah, it's not that easy. But remember, number of system calls available is 427, and that was 0x, 1AB, and hex. And the original sysentry table is at number of sysentries plus 32. So we can look at the mock kernel image, and you see I have a highlight there. We have the number of sysentries, and 32 bytes ahead we have the start of the sysentry table. So all we need to do is we copy the kernel image into a buffer. We find the offset to the end sysent symbol, and we add 32 bytes to that offset and return a pointer to that position. And there we have our sysentry table from disk, which is sort of unknown state. It can be modified. Attacker could hook open call to the kernel image and whatnot to make you read another sysentry table, but it's simple and it works. So here's the code for it. Just open the kernel image and do a for loop basically with a pointer and look for patterns. So if you run that, you should find it. Demo time. Fingers crossed. So we build the rootkit and the detector. So we patch the kernel, and you see PD11 is invisible again. We run the detector as 2 modes, scan and restore. First we scan. It detects 2 hooked system calls. And we run restore. 2 restored system calls successfully. And PD11 is invisible again. So that's basically it about detection. But as I said, this is not reality. It works in a lab, but you shouldn't rely on this. We could go back and do the other demo also. We have time. This is basically an open hook for the open syscall, which will take a path and a flag. And if you specify a magic flag, the file won't be open, but it will be executed as root. So now we patch the kernel. In temp, there's a file called runme, and we're just a regular user. And the runme file cats the master password file to temp pwn. The test program here just calls open temp runme with 1337 as the flag, nothing special, and then exits. So we run it and check the file, and we have the password file. Not that OS X stores shadow hashes or something in there, but it's read-only for root. So it's an easy way for a local backdoor to be implemented. And here's the other slides. Oh yeah, here. Articles on this subject, if you want to read up to it. You have Abusing Mach on Mach by Nemo, which talks about this a lot deeper, and the whole Mach XNU technology is a great paper. Mac OS X Wars, A New Hope by Nemo, Frac64. It's also a good paper on Mac OS X stuff. And Developing Mac OS X Kernel Rootkits by myself and Huawei. We talk a little bit about runtime kernel patching, but mostly about kernel extensions. So Mac Hacker's Handbook by Dino and Miller. It's a great MacBook if you love OS X and hacking Macs. Updated slides will be available on kmem.se. Perhaps some code. There already some code there, symbol resolving code, and some other I can't remember, but it's there. So that's all I had to say. You know where to find me. If you have any questions, I don't have any Q&A, so thank you.